Perfect. Thank you. I hope that I'm also audible online. Good morning, everyone, and thank you very much for the kind invitation. My name is Stefano. I'm a professor of cybersecurity at Politecnico in Milan, and I work in a laboratory called Next. Next is a laboratory about basically everything that has to do with system architectures, including cybersecurity. So the objective of the talk today is to introduce the research of my team on automotive security. The thing that I will do is I will go through several of our research angles, trying to introduce what I think is interesting about those. I have more materials than I will show that I will leave afterwards. So if anyone has any interest, we can discuss it later over lunch or whatever, or we can take questions. The title of the talk is that to break is easier than to patch. Because during our research, what I personally found on one side intriguing, on the other side challenging, is that while it is very easy to offer suggestions on how to break something and to patch that specific thing, I found it way more complex and way more challenging to figure out ways to design things so that they actually are more secure, because breaking and patching, as we all know, does not really lead to a significant improvement in security. Okay, let me see. So basically, this is an overview of the systems in cars. I will not spend too much time because I think that several of the people actually are already more than aware of it. It's just to point out what things we actually look at and what things we don't. Basically, we looked at both the actual onboard network protocols, and so we have a few items of research related to vulnerabilities in CAN itself. And we looked at several other items basically in compromising components of the control units of the vehicle. More recently, we have started looking also at the V2X connectivity. We have more preliminary results on this. I think that today, given what I have seen on the other speakers, also presentations and focus, I will be mostly focusing on what we did in the vehicle networks area. But of course, if there is interest, we can talk also about other parts. So this is actually a research challenge that points at the what I introduced as the title of the talk. It is difficult to figure out ways to improve at the design level how you can design networks of vehicles so that attacks are less likely to succeed or more difficult to achieve. Our approach in trying to figure out a possible approach to this problem was to look at the topology of networks. Why topology of networks? Because if you think about it, basically that's this architectural design thing that you can apply across different vehicles, as opposed to how to patch a single ECU or design a single system. The insight here was that basically we looked at a way to simplify the problem. And it turns out that in our mind, the best simplification that you can do for this problem, it's resorting to represent attacks as attack trees. In fact, most of the attacks that have been shown on vehicles are more or less the same attack. yes, the details change. Yes, the actual realization on real-world vehicles is very challenging. But in the end, most of the attacks have the very same goals. It's not, a vehicle is not such a complicated system from the attacker goal perspective. An attacker may want to basically steal the vehicle, make the vehicle drive unsafely, steal some personal information that are connected to what the vehicle has recorded, impact the, shall we say, the brand side of things. So impact the brand in making it perceived as unsafe, or impact the brand because it steals secrets in the design of the vehicle, if any. But this has been done with reverse engineering for a very long time. So it's not like it's a novel cybersecurity issue. So there's just a few things that an attacker may want to realize. And these few things can be done in very specific ways, regardless of the specific vehicle that we are looking at. So for instance, if you want to cause an accident, there's just a few ways that make sense in an attacker's point of view to make the vehicle unsafe to drive. In order to do these things, you basically can break down what an attacker needs to do in a number of components of ECUs that the attacker needs to compromise. So basically, you can map the attack trees in attack paths on board the vehicle. Since the vehicle has a few well-defined points of entry, the e-call box, the firmware update unit, the head unit were connected to entertainment systems and so on, you can basically derive automatically topology modifications of the onboard CAN, so ways to break up CAN that preserve the functionality constraints. Which areas of the CAN need to be high performance enough to support certain communications and so on. And at the same time, make it as difficult as possible for an attacker to actually compromise in a single run all of the devices they need to compromise to achieve those specific attacks. So we basically created a way to do this automatically. The way we tested that this approach was sensible was to take examples of vehicles that had been compromised in literature and modifications that had been proposed by automotive engineers in order to fix those vulnerabilities, and see if our software would derive something that is not exactly the same, because of course the human-derived modification is always different, but that maps to it reasonably well. So this is an approach to try to bring the security of vehicles from breaking and patching into automatic design. Unsurprisingly, no one does this. Why? Because vehicles are not really designed from scratch, right? Vehicles are designed based on previous vehicles. And this makes it unappealing when we as academics propose a solution that is actually beyond the patching. If you look at the history of vulnerability disclosure and the reactions of the industry to vulnerability disclosure in automotive, you find two types of results. The first type of result is not caring, because everyone has started talking about automotive cybersecurity after Charlie Miller and Chris Valasek drove a journalist into a tree from another state. That's when everyone started talking about that. But that experiment was exactly the same experiment that the guys at UCSD had done 5 years earlier. The problem is that the guys at UCSD drove the car and manipulated it in an airport with only PhD students on board, so no one cared. If you want people to care, you need to place a journalist, not a PhD student on board. I'm sorry, PhD students know that they will get sacrificed for this. But the that's the one thing, right? And then in those cases, what happened is that the industry patched the specific vulnerability. So Fiat Chrysler literally shipped every one of the 2 million customers that had the vulnerable car a USB key that would update the specific firmware of the specific ECU. So basically training all their customers to put any USB key that arrives in mail in their car and letting the car update itself, but that's another story. And that's it, patching that specific vulnerability. Because redesigning has a cost that is very high, which is the same reason why people walk out of the room every time an academic says, oh, we have redesigned CAN to protect against this. And automotive engineers walk out of the room because, of course, no one is ever going to redesign CAN. If anything, sooner or later, parts of automotive engineering will move to automotive Ethernet, but they will never patch CAN. Which is the reason why we and a lot of other colleagues have offered intrusion detection systems to put on vehicles. Now, I put this here in order to mention it so that if anyone is interested, you can go and look at the results. I will not spend time on this because I have a limited time slot and there's other things that I want to talk about, but I left this as documentation. But this is actually the area that in academia has produced most results. So most academic papers about automotive are, we took a data set of CAN and we applied machine learning to it. This is basically the research. And the problem with this research, which I am also guilty of, so I'm talking about my research first, is that it is pointless. Because suppose that for a moment, that intrusion detection systems based on machine learning actually worked. They don't. I can say it. My PhD thesis was on those in 2006. They didn't work then and they don't work now. But even if they did, even if we had a perfect intrusion detection system to place on cars, what good would it be? Do you place a hacker blinker light on the dashboard, oil, engine, fuel, hacker? And when the hacker light turns on, what does the driver do? Park the car and run away from it? Intrusion detection systems on cars have a role, but it's a very limited one. Their role, for instance, is in detecting attacks on a fleet of cars so that the manufacturer can investigate and figure out a solution for the next attack. That attack is gone. It has happened already. So there's a role for this, but these are not going to solve a problem. They don't solve any problem, they cause it actually. Okay, so I left here some data about that. Now, let me talk instead about where intrusion detection systems, besides the fleet-wide thing, may have a role. So, CAN is a kind of a shitty protocol. And one of the examples of why it's a bad protocol is a series of attacks that actually I caused because I let a master students play with CAN, and that's always a terrible idea. Because CAN is a protocol that is subject to a type of, it's not really an attack, it's a type of fault called bit banging. Since it's a differential voltage protocol, you can overwrite ones with zeros. So this is a non-trivial consequence for intrusion detection systems. Since this overwriting happens on the wire, unless a system has been specifically designed to detect the artifacts that come out of this bit banging attack, there's no way to detect it. And an intrusion detection system working at the application layer, for the lack of a better term, so working at the ECU level, is not going to detect this because this happens on the transceiver. So it's invisible for an application layer detector. Just to give you an example of the type of attacks that can be performed with bit banging, because of course there's a trivial attack that can be performed, which is flooding the CAN. If you are on an ECU in the vehicle, you can always make the vehicle's CAN unreliable and useless. That's a given. It's not really preventable. But what we found is that there is actually a way to deactivate a specific ECU with a targeted attack. So to silence one specific ECU on the vehicle if you are connected to another ECU. And this is due to how CAN handles the errors. Basically, when an ECU talks on CAN, since CAN does not really have an access control mechanism for the media, what the transceiver of the ECU does is it writes on CAN, and at the same time it reads on CAN. If it reads the same thing it's writing, it supposes that everything has gone through. If it reads different bits than the bits that it's writing, it means that someone else is talking at the same time. And so they back off, and there is a way to decide who has a priority. However, if this happens many times, where many is defined by the protocol, if this happens many times, the transceiver needs to realize that probably it is broken. It's trying to transmit and always receiving a different bit than it is transmitting. At some point, it needs to realize it's broken. It's pointless to keep trying to transmit. It's just flooding the bus. And so the ECU is, by standard, supposed to go in a status called as bus off, detaching from the bus and not writing on the bus anymore. Which, of course, for critical ECUs is not something that is desirable, but it's something that the protocol mandates. It should happen very rarely, because this should happen only if the transceiver is broken, which is kind of not really common. But an attacker can make that happen, because they can do bit banging selectively only on that transceiver every time that transceiver talks. And so in a paper a few years ago, 6 or 7 years ago, we demonstrated that this could happen on an unmodified ECU once someone was on the ECU. Sorry, I meant this can happen if someone is on CAN, hardware connected to CAN. There is a demonstration here on a video that you can go and look at afterwards if you like. It's on the Alpha Juliet of the master science student. He didn't kill himself doing this. I'm very proud of that. We designed a detection mechanism that actually has been implemented by some parts of the industry, specifically for this. So by making use of how the protocol of the rules that the protocol uses for counting this type of errors, by modifying by making a count that is modified in a specific way, we are able to tell, oh, this is not a broken transceiver. This is someone actually overwriting. So we did this. In the industry, someone implemented this, but many companies did not, because of a reason. As I was saying, our attack was demonstrated by physically connecting to CAN. And in our paper in 2014, we said, but we were not listened to, oh, this can, of course, this can be done also if you are on an ECU. Now, the of course turned out to require 2 years of research. It was an of course, but we were kind of optimistic about that. But of course, this can be done. So we have this new paper that is at CCS in a month, which shows that you can do this from an unmodified transceiver of an ECU on board the vehicle. So as long as you are attested on the vehicle, you can do this. You can make the ECU run the attack to selectively disable something else. Or in general, you can make the ECU run any bit banging attack that you want. And this is done basically by abusing the fact that I don't know if you are familiar with the concept of a polyglot. A polyglot is a file that is a valid file in multiple types. So you may have a PDF file that is a valid PDF file that you can open with a PDF reader, but is also an executable file that you can run. There's a colleague, Angia Albertini, that works for Google, that is a worldwide expert on polyglots, and he has generated polyglots that do magic things. This is a polyglot on CAN. There are ways to create frames that mean different things to different controllers. And these can be exploited to perform this bit banging attack, even if the controller should not be able to do that. And so this is a more general thing that we have shown. Actually, the first version of the paper was severely rejected because the reviewers didn't like the fact that we said that we were creating polyglots on CAN. And so we are not creating polyglots on CAN. We just demonstrated that they can be done. This was a very important specification that caused us to shift from one top conference to another. I'm really pissed off about that. I mean, reviewers too, right? But actually, while we used this in order to demonstrate that our of course in 2014 was really of course, it can be used, abused to the same concept can be abused to do a lot more than this. Probably we don't really have a complete idea of what can be done, but we have demonstrated this on real world platforms. There's a few limitations that probably a real world attacker would need to to walk around. If you want, even if the paper is not out yet, I can share with you the preprint. It's actually a pretty interesting work. I can say that because my PhD students did it, I didn't, so it's I can commend it without commending myself. As I said, another area that is of interest, and then I will really stop on this, but is the area of V2X communications. Now, basically, this paper was born in a very specific way. I am a very sarcastic opponent of blockchain, and a colleague that works on blockchain dared me to find an application for blockchain that I would not complain about. So this is what came out, which is a way to use a distributed ledger, but it's not really a blockchain. We could have done this with distributed data structures a long time before blockchain. It's a distributed ledger to approach the problem of how do we get vehicles talking to each other or talking to roadside units that are not necessarily all in a same authentication system, which if we want to use V2X, it's probably the use case that is most general, so that we can make use of that information for not really safety critical maybe, but for important decisions on board the vehicle without requiring central authorities. And basically, we showed an architecture where you use a distributed ledger to record a value of trust. So seeing how trustworthy is a vehicle when it says, oh, okay, so this part of this patch of road is in icing conditions, or this other vehicle is moving at this speed. How trustworthy those information are, collecting a trustworthiness information in a distributed way with proof of stake through a network of vehicles that do not necessarily know each other. It's a very interesting problem, and the interesting part about it is that you can, while you experiment with it, you realize that in order to fully exploit V2X to communicate items that are security or safety relevant, there is a lot of work to do. The analysis of the background of how this has been approached is that since most of the work done in V2X is in the protocols themselves, our colleagues that work on it have basically taken for granted that in a way or another, there is going to be an authority to validate who everyone is in a scheme. But this is probably not true. If you think about it, this is something that has already been approached in other areas in the past, in particular in aviation. If you look at ADS-B, the protocol is completely open. And as a result, the information produced by the protocol need to be validated otherwise before being used for safety critical actions, because there is no central authority. Since the design of the architecture is based on the fact that there is no central authority, in order to make ADS-B devices cheap and installable on all of the 500,000 general aviation planes that are out there, because the benefit of having an open approach enormously surpass the security challenges. But this works because in aviation, you have other sources that you can use to validate that. In vehicles, this is not necessarily the case, but the constraints is the same, because if you want to do this with a centralized authority, you need to define who the centralized authority is, or you will end up having vehicles in different fleets that do not really talk to each other. At this point, it's not a vehicle-to-vehicle communication, really. You do not exploit fully the benefits of this. So it's a very interesting and challenging problem that we have started looking into. If anyone is interested in discussing that or aviation protocols, I would be happy to do that. Thank you very much for listening to me. And I'm going to be here, so if we want to talk about later, because I think I need to give way to the next speaker. Thank you very much.
Thank you very much, Stefano. If you have a quick question, you can ask now. We have a long lunch break.
That's actually, so I will repeat it because I think otherwise people from home do not hear it. The question was about how important is the protection or the change in topology in protecting a vehicle. I think it's important, but more specifically, the reason why we focused on topology is not because of the importance, but because it's the one element that OEMs, that manufacturers of cars, can really work on, because the end design of the communication protocols and of the ECU software, they usually offload to tier ones around, and so they may not control that. Instead, the topology is the one element that they actually kind of control and can dictate. But it is important because if at the moment the topology and the different parts of CAN are connected by basically what we would call a proxy device in the middle, which is designed for just for application purposes. Most in the past, they have never been designed for security consideration. But those are checkpoints where you could add security considerations that can be made by the OEM even after some parts of the onboard networks have already been designed. So they can be applied even if the tier one has designed this thing without involving the OEM at all, which is a challenge in automotive engineering. So thank you for the question. Thank you very much for listening.
Thank you very much.